The presenters tonight will be myself, Tim Haley, Paul Meyer, David Hintz, Grant Gillian, and Rob Lennert. We also want to give a good shout out to Eddie Shields, who couldn't make it tonight. He is retiring, and he's been one of our great team members. And we just want to thank him for all his service, for supporting the briefings. And welcome to Dirty Dozen for helicopters. Tonight, we're going to go over the Dirty Dozen. We're going to do a little bit of information on the human error and maintenance causes and death and destruction. We're going to identify the 12 causes of maintenance error, and we're going to suggest how to reduce maintenance error. Also, there are 5 handouts within the GoToWebinar menu that you can grab of some good information that you may want to share with your friends that are in helicopter maintenance. This is a really good slide. The best people make the worst mistakes. I want you to know I couldn't find any good pictures of anyone ejecting out of a helicopter, so I had to use this fixed wing example. Human error is both universal and inevitable. This means everyone will make a mistake sooner or later. In fact, the best people often make the worst mistakes. When learning of an accident caused by human error, it is common to think the person involved is somehow deficient in skill or character, while we, on the other hand, are well-meaning, motivated, experienced technicians. We just wouldn't do something that stupid. When we think in these terms, we discount the moral of the story and miss the lesson in it. This is a picture of a spectacular accident caused by human error. The pilot started the loop at about 1,000 feet, 100 feet lower than he should have. Before takeoff, apologize for the background noise. Before takeoff, the pilot set his altimeter to his home base field elevation at Nellis Air Force Base. His action perhaps was the result of habit. The elevation at his air base that he was at was 1,100 feet higher than Nellis. Even though the mistake was slight, setting the wrong altimeter setting, the outcome was tragic. Here's the lesson. Does the Air Force select mediocre pilots for the Thunderbird demonstration team? Not likely. They choose only the best of the best. The reason people make the worst mistakes is they're assigned the riskiest job. The point is you can be the sharpest person on the crew, but if you've had a sleepless night or someone doesn't give you vital information, then you may make a mistake. It may be a very slight mistake, but in the context of aviation, even a very slight mistake can be disastrous, perhaps even fatal. Good people make mistakes because they're influenced by their organization, workplace, tools, and environment to do so. The objective of this presentation is to introduce 12 common issues that influence humans to make mistakes. And additionally, error capture strategies called safety nets will be suggested, which may prevent common errors from having tragic consequences. Okay, well, or maybe I did find one ejecting from a helicopter modified by rotor floater. Not true, but an April Fool's article from 2015. So don't publish that picture anywhere and tell them it's a factual picture. So how do we prevent mistakes like this one? How do we break the chain of events that may well result in the loss of an aircraft or, worst case, a fatality? The Dirty Dozen is a poster series highlighting 12 preconditions for unsafe acts. In other words, factors that influence people to make mistakes. The series of posters was developed by Gordon DuPont while working with Transport Canada. It's not meant to be a comprehensive list. It's just meant to stimulate the human factors discussion. Okay, so this is our first case study that we're going to cover for the Dirty Dozen. It's actually going to cover most of the Dirty Dozen. I would say maybe about 7 of the 12 Dirty Dozen are going to be covered by this one accident. Okay? So on July 28, 2010, at 13:42 Mountain Standard Time, an Air Methods Corporation American Eurocopter AS-350B3 medical helicopter, November 509 Alpha Mike, during a VFR flight, under Part 91 descended rapidly and collided with terrain in Tucson, Arizona. The aircraft was substantially damaged and consumed by a post-impact fire. The pilot and 2 medical flight crew members were fatally injured. The repositioning flight was for engine coking originating at the Marana Regional Airport in Tucson, Arizona at 13:32 hours, and the intended destination was the Air Methods Base in Douglas, Arizona. This is the actual crashed aircraft before the crash, of course. And just to let everybody know, this accident that I actually went in, I dug into the NTSB database, and there are actually attachments with all kinds of background data to include the technical manual pages they use for the investigation, photographs of the aircraft. There's a lot of good information on the NTSB website. And this is I'm going to go ahead and read this. This is what it looked like at the accident scene. External examination of the engine at the accident site revealed that the fuel inlet union was detached from the boss on the compressor case. The fuel supply line remained attached to the union and the hydromechanical unit via the adjusted valve. The intermediate gasket was located in the fuselage debris directly below the union. And we will cover all of the details behind this accident, and we'll actually show you what all of those parts look like. The first item we're going to cover on the Dirty Dozen is lack of communications. And some of the safety nets you can use is you can use logbooks, worksheets, do a good thorough shift turnover, discuss the work that's been completed with the people who need to know, and always ask yourself that question, who needs to know this information? And never assume anything. Always double check your work, remove the inspection plate, and ask your teammates to explain. This is probably one of the toughest Dirty Dozen for all of us as mechanics to make sure that we do. Okay, we're going to cover a document that the FAA uses very often. I'm going to give you a little bit of background on that. In 1953, the Civil Aeronautics Board, or the CAB, revised the Civil Air Regulations to require that each operator apply for an OPSPEC, or Operation Specification, at the time of application for an air carrier certificate or an air agency certificate. Air carriers that existed at the time were issued OPSPECs to be used instead of the competency or temporary letters. The OPSPECs provide an effective method for establishing safety standards that address a wide range of variables. In addition, OPSPECs can be adapted to a specific certificate holder or operator's class and size of aircraft and different kinds of operations. Let's review. We're going to discuss the Dirty Dozen. And so look at this. So on the slide, you see lack of communication between the FAA inspectors and the repair station. So when the investigation was conducted, the FAA principal maintenance inspector stated he removed the work away from station authorization for the repair station that supported Air Methods. The owner of the repair station stated he did not identify the changes when he signed the page of A004 of the OPSPEC. So you ask, what does OPSPEC look like? This is what they look like. And they're issued to any operator or agency. When we talk about operator, we could be referring to an airline, we could be referring to a charter operator, or we can be referring to an air agency, which is a Part 145 repair station. Okay? So here's the example. The red arrows point to the paragraphs issued in this situation. So you're actually seeing what the OPSPECs look like for this type operator. A004 is like a table of contents for OPSPECs. It lists all the OPSPECs that pertain to that operator. And you notice over here on the right, I've got an arrow pointing to Delta 100, which means it was issued the ability to operate, perform work excluding continuous operations at additional locations other than its fixed location. A101 is perform work including continuous operations at additional locations other than a primary fixed location. So if you look over to the right, this is the D100 paragraph that's issued, and down under Alpha and Bravo gives you whether they can or cannot operate continuously. So if you read Bravo, you're going to see the certificate holder may not perform continuous operation at a facility other than a station's fixed location. So the reason I have this slide in here is because I'm just showing how this is a document that pretty much is a little hard to understand, but there was a lack of communication at this time between the FAA and the agency. Even at the FAA, we make mistakes. And so this is just a good example where the communication wasn't good between the operator and the FAA. The next dirty dozen we're going to cover is complacency. It can be caused by a lack of sufficient stress. We hear stress is bad for our health, and too much unresolved stress certainly is. However, we need a moderate amount of stress for optimum performance. Okay? While too much stress causes confusion and fixation, too little stress can be a problem as well. It can cause a person to be bored and complacent. The following example is a case where a complacent person's mistake had dire health consequences. Okay? And everybody's experienced this in life. When you get really stressed out, you get frustrated. But when things are so relaxed, sometimes it can and cannot be good. And so let's go ahead and cover that dirty dozen. Okay. Here's the example of complacency. The Turbo Mecha service. I want to mention one thing real quick too. All of these organizations are professional organizations that we use for these case studies. They're very professional. I myself worked for Air Methods for many years, and they were very professional, very organized in what they did. And so this is not a knock on any of these organizations. I just wanted to mention that real quick. As a Turbo Mecha Service Center, Helicopter Services of Nevada provided levels 1, 2, and 3 maintenance service, parts, and tools. The Turbo Mecha Service Center technicians completed a Turbo Mecha design checklist and engine build when performing field maintenance. Turbo Mecha, who makes the engine, does not require its outside service centers to document their work with the forms, and they are allowed to develop their own forms to document work. Helicopter Services of Nevada developed their own work order forms and checklists that were completed when work items were accomplished. In the interviews with the HSN mechanic, he reported that when an in-house inspection is performed, they used an FAA 8130-3 form, the work order package form, as well as a final inspection that was completed. He reported that when mechanics are working in the field, they don't complete the 8130-3 form and do not do the thorough inspections and paperwork that occurs when engines come into the repair shop due to the specific nature of the field work items requested. This means he was the only person to look at his detailed level 3 maintenance he performed and did not ask for help from the other Air Methods mechanics 20 feet away from where he could have. And that's why I'm saying this could be considered complacency. When you're doing something this detailed, you may want to have someone look behind you before you put cover panels on an item that can't be inspected once you cover it up. So the safety nets that you need to remember on complacency are, we need to face the reality that our industry's mistakes, even slight ones, may kill someone. Some of the safety nets you can implement are physical fitness, which, you always feel much better after physical fitness. It helps you think clearly. It makes you feel good. Create challenges for yourself. Challenge yourself to find faults every day. Never sign for anything you didn't do. It's also an ethical decision you have to make sure you're doing when you don't sign for something you didn't do. The next item we're going to cover on the dirty dozen is lack of knowledge. Okay? And you may think lack of knowledge is about inexperience. However, the rational point of view is that aviation is incredibly complex. No one has all the answers. We might all lack knowledge in tasks that are not familiar to us. Even experienced people need to refer to up-to-date manuals and ask questions. People can be very sharp and very well-meaning, but if they are untrained, bad things can happen. Even in this presentation, I had to call my guys I used to work with in Air Methods and ask them questions about the engine because I couldn't remember all the stuff that I used to do back in the day when I was a relief mechanic for Air Methods. Okay, lack of knowledge. This is actually for the pilot. So here's what happened. The Marana duty pilot performed a ground run of the helicopter. This is after all the maintenance was done. And they found that the engine's hydromechanical unit was found to be leaking. The next day, on July the 27th, the HMU leak was resolved and the pilot again performed a ground run. The ground one came out good, and the pilot then asked for permission from the area aviation manager to put the base out of service while he performed the post-maintenance flight check. The Air Methods AVL hub interface, I'm going to assume this is a computer system that tracks how long the aircraft flew remotely, recorded that the maintenance test flight occurred on July 27th from 1743 to 1750 hours, and that's just 5:43 p.m. to 5:50 p.m. It's just converted into military hours. So we're talking a total of 7.5 minutes. According to the pilot, the following items were done during his maintenance check. As you can see by the slide, he did a droop check, a rate of climb check, a cruise power check, a flight limiter indicator check, a flame out check, and an auto rotation. Now, 7.5 minutes doesn't seem very long for all those checks, but that's what the system recorded. And there were no actual written records of that test flight of exactly what he had done. But the AS350B3 flight manual, section 8.3.2, contains a matrix that illustrates what post-maintenance flight checks need to be performed for various maintenance actions or component replacement. For maintenance on an engine, a FAADEC, or a module, the following checks are to be performed after the ground run. As you can see on the slide, a hover flight, a max continuous power climb, a max takeoff power check, a max continuous power level flight. The chief pilot at American Eurocopter stated that these should take between 30 and 45 minutes to complete. Okay? Now, what I will say is this pilot that did this test flight, he did not realize he was doing the incorrect items. So what I would say is for mechanics and pilots, always check your manual. And if you're not sure, always go to some expert or mentor who knows more than you and ask them where it might be in the manual. Okay, the next item we're going to cover is lack of knowledge. Here's some things you might want to consider. Get training on type. Bad things happen to untrained people. Put yourself in the place of the maintenance test flight. He was trying to save the company money by saving hours, cycles, and fuel costs. His motivation was not in doubt. His method leaves a bit to be desired. He probably would have liked to know what should have been tested after an engine disassembly and reinstallation of a turbine engine on an AS350B3. So recommendations or your actual safety nets are going to be stay current, read up-to-date manuals, trade magazines, websites, and human factors information. And I tell you, I appreciate you guys being on this webinar because it shows that you're trying to stay current. Use up-to-date manuals. Also, ask a tech rep. Tech reps are actually very approachable and will help you in a lot of cases if you get stuck on a situation. So definitely get in touch with them and communicate. Humility will make you go a long ways in aviation. I had to swallow a lot of humble pie in my career. Thank God I did because I needed to. I learned a lot when I did that too. So the next item for the Dirty Dozen is distraction. Does anyone have a cell phone? It's become a feature of our culture, whether we're driving, listening to a speaker, or maintaining an aircraft. In some cases, it can be disastrous. Our jobs and our lives are full of distractions. A distraction shifts one focus from the job at hand and increases the potential for a prospective memory or place-losing error. Distractions can come in many forms such as noise, bright lights, people, radio messages, telephone calls, horseplay, and problems at home. This example, though, is going to be an interesting one for you. So on September the 16th, 2017, at about 4:35 Mountain Daylight Time, a Bell 206 L-3 helicopter, or a Long Ranger, November 213 Tango Victor, impacted terrain near Ancho, New Mexico. The pilot, the sole occupant, was fatally injured, and the helicopter was destroyed. It was a flight that had originated at about 3:45 p.m. from Roswell International Air Center Airport in Roswell, New Mexico, destined for Albuquerque International Sunport in Albuquerque, New Mexico. So let's just review the slide real quick. He was doing a cross-country business flight and a helicopter, and the weather was good and visibility was at least 10 miles. So, everything was just as clear as could be. The last 5 minutes of the flight, however, the helicopter's GPS altitude varied between 6,200 and 6,456 feet. But the terrain in the incident or the accident area was between 6,000 and 6,400 feet. The impact point was at 6,330 feet. Anyone want to guess what happened? Note, this is about distracted. The pilot's cell phone was recovered, and a review of the phone records revealed that at 4:12 p.m., he called a rental car agency. An agency employee stated that she remembered the call well. She added she could not tell that he was in a helicopter, but that he seemed busy or distracted. And that, as they were talking about a future rental, and she was, mid-sentence, the line was disconnected. Interesting. No matter how you look at this accident, it was caused by a distracted person who was attempting to save time, but was not in a good situation to use the device. As you can see by the slide, you can assume he was distracted by a cell phone. Okay? Here's what I would recommend. It's best to use the communication systems in your aircraft since they're designed to be used during flight. And I'm going to let you guys know, and y'all know this, in a helicopter, you don't have many limbs available to do things with. A handheld cell phone is not designed to be used by a pilot in an aircraft. One other consideration is most important is that helicopters have 3 controls. A person should be operating these with their limbs. If there's any non-helicopter people out here listening, just for your information, one is the collective with one hand. The other control is the cyclic in another hand. And the other is using their feet to operate the tail rotor pedals. So how can you operate a phone with all your arms and legs in use? Okay? Yeah, you can't. I feel bad for this guy and his family. I really do. But let's know saving time is not always worth it. Okay? Next up on the Dirty Dozen is safety nets. Don't use cellular phones while conducting maintenance or while flying an aircraft. Don't try to do 2 things at once. Always finish the job or unfasten the connection. In one of the cases described earlier, finishing the job by torquing the hardware could have prevented the accident. The alternative would have been to leave the connection unfastened. That would have also prevented the accident. The engine would not have started if the fuel line was disconnected, or he could have marked the uncompleted work by hanging some wire or maybe a removable for-flight tag. You can lock wire where possible or use torque seal. You can double inspect by another or self. You can use a detailed check sheet. When you return to the job, always go back 3 steps if you have to stop at a certain point. That's a great recommendation. The next item up on the Dirty Dozen is lack of teamwork. Okay? As mechanics, we're used to working alone, so the concept of teamwork can be a real change in thinking. And I say this because there are some isolated bases out there. I'll give you an example. If you're out there and you're in Alaska and you're a single person at your base, you don't have anybody to look behind your work. So you're going to have to look and have yourself as a double checker. Just remember that, okay? But if you have a pilot, you can always have them check. So, consider that when you're using teamwork, and always communicate. And here's the example for lack of teamwork. Between 24 July and 26 July, the accident engine was disassembled first, and the mechanics realized they would need additional parts and tooling to complete the work. The accident engine was set aside, and the second engine was disassembled and the fuel manifold replaced. As the Air Methods mechanics completed the work on the second engine, the HSN, or repair station technician, replaced the manifold on the accident engine. During the work on the accident engine, Module 3 was disassembled. The fuel injection manifold was replaced. The engine reassembled by just the HSN technician, or the repair station technician, including the fuel inlet union. The engine was reinstalled into the helicopter by Air Methods maintenance personnel. The HSN technician inspected his own work, and as an HSN technician working away from its fixed location, he had the authority to inspect his own work. So just remember that. This is one of those situations where the HSN technician was within his legal authority, but let's ask that question on the slide. What would have happened if he would have asked the Air Methods mechanics to check his work before reassembly? Oh my gosh, this whole incident would have never happened. It's easy for me to say that in the after, knowing all this information, but when you're in a detailed work environment like that, where you're digging into an engine and reassembling modules, that's pretty complex work that we all have to do, and do safely. So let's continue on with this. This is the more information on what happened with this accident. This is the as received parts that are displayed in the upper figure. So these are all the parts that were found at the accident site, which is the fuel line, the jet union, where it would be attached to the diffuser assembly with a copper gasket between. So these are the items that were intact but reportedly found disconnected at the jet union to diffuser connection. Note the bolts. The manual calls them screws, but they're technically bolts, and nut hardware were not found at the accident site. So these are new examples of the components that were received for comparison. The detail A and picture displays the exemplars of the jet union associated attachment hardware. So the items that they couldn't find were the mounting bolts and nuts. Okay, those were the items that were missing. We can only make an assumption that the mechanic may have finger tightened them and not actually torqued them, but we don't know for sure because they were never found at the accident site. Okay, let's cover the safety nets for lack of teamwork. Communicate. Go ask that person across the hangar to inspect your work before you put a cover panel on. Team's tasks require a full team. Eat some humble pie. I've made mistakes in the past where I had to eat humble pie, and it's always a good idea to have someone look at your work. Follow the correct procedure and reconfirm those duties among team members. Those are some good safety nets to remember for lack of teamwork. The next item we're going to cover is fatigue. Fatigue is a constant threat to all of us. There are three types of fatigue. Acute and operational fatigue are really the same thing. They're caused by hard work and long hours. It's really only a matter of duration. Chronic fatigue is something that requires medical intervention. It is depression and needs at least counseling and possibly medicine. Symptoms of fatigue. These symptoms are true of fatigue people regardless of the category of fatigue they're experiencing. Chronic fatigue and chronic pain are similar in that they exhibit similar symptoms. The symptoms are often more evident to those who are working around the fatigued ones than it is to them. And that is definitely true. I've worked in environments where we've had to stay up long hours in the military, and you'll notice that when people become fatigued, they'll start slurring their speech. They'll start making a lot of mistakes. And so be on the lookout with your coworkers and let them know if you see them fatigued. And this is a really interesting slide. We're going to cover this accident here in a little while, but this is a chart that is an example of how you can compare fatigue to the impairment of blood alcohol effects. Blood alcohol concentration levels represent the percent of your blood that is concentrated with alcohol. A BAC of 0.10 means that 0.1% of your bloodstream is comprised of alcohol. So let's look at this slide. Would you go to or stay at work if you were awake for 17 hours? That example is equivalent to a 0.05% blood alcohol concentration. 22 hours is equal to 0.08%. 24 hours is 0.10%. One thing that's interesting about this slide is all three of these, well, I say all three of these, all of these would exceed most of the country's limits. So it concerns me, especially when you get to 24 hours, there is no country that you would not be considered impaired in with 0.10%. This slide covers fatigue issues, and we're going to cover this, like I said, I mentioned this earlier, we're going to cover this case study later on in the slide presentation. Tim Haley's going to go over it. But here's some examples of a mechanic and inspector and the duties that they pulled. In this example, the mechanics had a normal shift, and their bodies were used to that, okay? That circadian rhythm was set to these schedules. In the example we're going to cover, they were supposed to be off the day that they worked. And the day that they worked, instead of working from 12 until 2300 hours, which would be 11 p.m., they worked from 0550 a.m. to 6:46 p.m. at night. Okay, that's a long day, and they're really close to each other. But the mechanic claimed he only got 5 hours of sleep, and the inspector claimed 7 hours of sleep. And again, like I said, Tim Haley will cover this accident on this AS350B2 coming up. You know, I've been through this also with heavy maintenance when you're trying to get an aircraft in and out. I'm sure you probably have too. This is the circadian rhythms I just mentioned. Most of our bodies have an internal clock with that 24-hour cycle. Our bodily functions cycle about these daily circadian rhythms, such as blood pressure, heart rate, core body temperature, and others. Perhaps most important is that our performance also cycles about this normal circadian rhythm. The typical circadian cycle causes performance to peak between noon and 9 in the evening and then fall to a minimum between 3 and 6 in the morning. The U.S. Marines did a test on this. They attempted to adjust their circadian rhythm, but it didn't quite work for them. That's why you see this tilt rotor with Marines jumping out the back. Some of the safety nets that you want to make sure you're aware of for fatigue is be aware of the symptoms and look for them in yourself and others. I mentioned this earlier. Sometimes it helps to notice it in others because when somebody becomes so exhausted, they don't realize that they're slurring their speech, they're having problems speaking, and they're having problems thinking clearly. Plan to avoid complex tasks at the bottom of your circadian rhythm. Sleep and exercise regularly. Ask others to check your work. Those are really, really good safety nets for fatigue. Okay, I believe we are ready to switch over, and we're going to have Tim Haley take over.
We're going to talk a little bit about lack of resources. I think we've all probably ran into the issue of lack of resources. Parts availability is certainly important. However, to expand a topic of lack of resources, what would be a list of important resources? How about money? Parts are expensive. What about people? Mechanics called in sick today. Supervisors out. How about time? Deadlines to meet. Tools, specialized tooling, we don't have it. Data, we don't have the proper manuals. Lack of resources may have contributed to a maintenance error, process errors. Engine was disassembled and the mechanics realized they didn't have the parts or the tooling to complete the work. The accident engine was set aside and another aircraft engine was worked on by the air methods mechanic. The accident engine was then worked on by the repair station mechanics. You know, it seems like we're picking on this air methods, but this one is a good example of the chain of events. There was a lot of different breakdown in the dirty dozen that led to this accident. The HSN technician inspected his own work, and as the HSN technician working away from its fixed location, he had the authority to inspect his own work. The air methods mechanic stated that they did not specifically inspect the HSN technician's work. However, they did inspect the engine after it was installed into the helicopter. Federal Regulations Part 135 does not require an independent inspection of maintenance. So what's the safety nets that we could have used for lack of resources? Check suspected areas at the beginning of the inspection and AOG the required parts. Order and stock the anticipated parts before they're required. Know all available part sources and arrange for pooling or loaning. Maintain a standard, and if in doubt, ground the aircraft. That last one seems to be the one we all have the trouble with. Nobody wants to be the person that grounded that airplane. So let's move on to number 8, pressure. That's one we probably all felt right there. A certain amount of pressure is appropriate, but too much pressure can cause a technician to make a mistake. If there is a generic hazard in aviation maintenance, it would be pressure to produce. Pressure to produce causes a drift to the dangerous methods. Pressure to produce is where the shortcuts come in. Features of pressure to produce are completion of work desired, lack of resources, supervisor condoning unapproved action to get the aircraft underway. The end justifies the means. Releasing the aircraft with work undone. Signs of excessive pressure to produce are being asked repeatedly, how long is this going to take? Getting frustrated and angry during the job, wanting to go home. Mechanics felt pressured after the first engine run, after maintenance. The Air Methods CEO was coming in for a visit. The Safford base was out of service. No backup aircraft was available since the backup helicopter was in use at Douglas. Interviews with the Air Method mechanics and the HSN technician, they all reported feeling a sense of pressure to complete the maintenance and return the helicopter to service. The Air Methods area aviation manager stated there is some internal pressure on pilots and mechanics because they know if they are not getting enough flight volume per month, for example, 10 hours or less, then their base may be considered for closure. All the bases in southern Arizona area were doing okay. So let's take a look at this V-22 Osprey. The Bell helicopter, Textron Boeing helicopter, V-22 Osprey tilt-rotor aircraft was being ferried to a military base in Quantico, Virginia, when it suddenly plunged into the Potomac River while on the downwind for landing. July 20th, 1992, crash killed all 7 crew members aboard. The court of inquiry said that the fluid leak into the right engine may be attributed to maintenance errors installing an oil seal backwards on the torque meter shaft. But the report added that it could not conclusively determine that this reversed oil seal caused the leak. Thus, the possibility of other leaking seals or sources could not be ruled out. In addition, the report said ground testing with incorrect installed seals did not show significant leakage, but a leak did occur on another Osprey V-22 with an incorrectly installed seal, according to the government witness. Maintenance errors cannot be assigned with certainty, but is considered to be a probable cause factor. One member of the Court of Inquiry noted that the system used to conduct maintenance at Eglin lacked organization, defined responsibilities, and a formal reporting and documentation of structure. Secondary cause factors, the Court of Inquiry said, included ineffective quality assurance of the oil seal installation. The report added that procedures for the removal and replacement of the torque meter seal contained in the technical manuals were vague and introduced the potential for incorrect installation. The report said no design deficiencies were discovered which were unique to tilt-rotor aircraft, but suggested the following design changes. Drive shaft material changed to improve heat tolerance, new torque meter shaft seals designed to prevent backward installation. Just to give you a little bit of background on this, this is out of the Helicopter Safety Newsletter, Volume 19, dated July and August of 1993. This picture here shows you how the leak-in torque shaft seal, which would be leaking right here, how the leak there would be adjusted into the engine. The U.S. Navy Court of Inquiry conducted that the aircraft experienced multiple emergencies upon entering the downwind and that the primary cause for the mishap was a flammable fluid leak which was ingested by the right engine. This diagram depicts and shows you how the leak could have been ingested into the right engine. The results of the crash investigation also identified human factors, maintenance and design issues. The report said the Boeing organization at Eglin from July 18 to July 20 was inappropriately downsized, inadequate supervised, and was too focused on the departure of both the team and the aircraft to ensure satisfactory completion of the maintenance requirement. What dirty dozen do you think contributed to this accident? Short-staffed, lack of supervision, pressure to make departure time, didn't properly double-check their work, lack of knowledge, seal in backwards, design issues. There's several of the dirty dozen to come into play right there. So the safety nets for pressure, be sure the pressure is not self-induced. You know, how many times are we stressing ourselves by putting pressure on ourselves to meet a deadline that's not really that of an important deadline? Communicate your concerns. Ask for extra help. Just say no. That probably is the hardest one of those four right there. Just say no, because it's not in our nature as mechanics to say no, we can't get it done. We are can-do people. We want to get it out. You just got to remember, self-induced pressure can be self-reduced. The picture of the Coast Guard saving capsized boaters is a good example of when pressure is not self-induced. Anything short of life and death can be put into a perspective and dealt with in a rational way. All right, so let's talk about lack of assertiveness. Mechanics as a group are not assertive as we could be. We like to fix the plane and lead the conflicts to the managers. We don't like having people in our face. Our culture is can-do. Assertiveness. Note the range between passive and aggressive is along the horizontal axis of the chart, and performance is along the vertical axis. Assertiveness resides on the continuum between passive and aggressive. One pole is the passive pole. It's a place where the person considers others' rights to be more important than his own. Someone operating at this pole will compromise their standards to get the job done. The other pole is the aggressive pole, where the person considers their own rights to be more important than anyone else. This is where the person is offended and becomes angry. Angry people nearly always regret their actions after they calm down. Neither pole is productive. Assertiveness is between the two poles. That's the green lines. It is where both parties' rights are respected. It's a space allowing teamwork and synergy. So what's the safety nets for lack of assertiveness? If it's not critical, record it in a journey log and only sign for what is serviceable. Refuse to compromise your standards. If it's not critical, record it in a journey log and only sign for work that's serviceable. This is a Canadian safety net. We don't have journey logs. We have minimum equipment lists, MELs, or we have other things like CDLs to fly aircraft with in-op equipment. The idea here would be to follow the company procedures for dispatch an aircraft that isn't perfect, whatever that procedure is. Refusal to compromise your standards. This would keep you out all sorts of trouble. Not that it's pressure-free, however. Do what's right even when no one supports you. Even if you lose, you really win. Not only will you be able to live with yourself, you may even save a life. It might even be your own, for instance. Left lower picture. Let's talk about that for a minute. The Italian loadmaster, an officer asked him to exit the aircraft just forward of a spinning propeller. Is it possible that there are procedures or rules to prevent such a thing? More than likely there is. Would the aircraft commander have been very happy if the loadmaster had said in a respectful way, There's a rule that prevents me from stepping out of the aircraft door with the left engine running. Please shut down the left engine and I'll be happy to check the battery door. He probably would not, but more than likely he would have done it. In hindsight, do you suppose the aircraft commander wishes that the loadmaster had asked him to shut the engine down? Top right picture is a crash in Teverite, Spain. It is a communication error accident, but one person had an understanding of what was going on. The KLM flight engineer asked the captain, "Is he not clear then?" After repeating his question, the captain answered, "Oh, yes." "Is he not clear then?" Is not the most assertive of statements. Certainly not the cause of the accident, but who knows? Had the captain been in a frame of mind to listen to the engineer, and had the engineer been more confident, then perhaps the accident would have not have happened. Stress. Oh, here's a good one. Well, stress, it's a blessing and a curse. It's a blessing in that it is what motivates us to perform. Why do we do anything at all? We experience some kind of pressure to compel us to move. It can be pleasure or pain, but it is stress from some kind. We hear that stress is bad, but a moderate amount of stress helps us to perform at our optimum level. This is an inverted U curve, similar to the assertive chart. Note that the level of stress is along the horizontal axis of the chart and the performance is along the vertical axis. If stress is low, it causes boredom and complacency. If stress is high, then it causes fixation and confusion. For maintenance folks, it is probably a matter of confusion. I'd hate to think that a maintenance person would become so stressed that the survival instinct would kick in and he would freeze like a deer in a headlight. A moderate level of stress is appropriate. It causes the person to be prepared and ready to perform. A moderate level of stress may be a person's supervisor giving the order to, "Hey, you guys get busy." So what's the safety nets for stress? Be aware of how stress can affect your work. Stop and look rationally at the problem. Determine a rational course of action and follow it. Take time off or at least have a short break. Discuss it with someone. Ask fellow workers to monitor your work. Exercise your body. James talked about that earlier. Lack of awareness. Lack of awareness or reduced situational awareness can be an indication one or more other human factors issues are in action, such as fatigue or distraction or lack of communication. Here's an example how the lack of awareness caused some serious damage. Lack of awareness. Aircraft operated at just below gross weight, had 90% of required fuel for 2.5-hour flight, but flight was only 55 minutes, and it could have been a problem during auto rotation. Engine operated past cycles by AD prior to accident. AD 2009-9-3 required engine inspection at 500 cycles. Engine had occurred 515.28 cycles. Let me give you a little background on that. In the accident, pilots off called the LifeCom. He reported 2 + 55, which means 2 hours, 55 minutes of fuel, which equates to a fuel load of 90%. Mission fuel is usually 2 hours, and the flight to Douglas would have taken 55 minutes. Therefore, the helicopter would have landed at Douglas with a mission fuel load of 2 hours. A review of the maintenance record showed that on June 21st, 2010, the engine cycles had exceeded the inspection requirements outlined in the AD. The airworthiness directed was due at 600 hours or 500 cycles, which occurred first. At the time of the inspection, the engine had acquired 308 hours and 515 cycles. The company identified the oversight and complied with the AD. Let me give you a little background on that. Weight and balance calculations were done by the pilot using a spreadsheet program available at each base and tailored for each aircraft. The actual weight and balance calculations performed by the pilot for the accident flight was not recorded and was not located in the wreckage, presumably destroyed. The spreadsheet program designated for the AS-350B3 dual listed a helicopter's weight at 3,329 pounds. The pilot's weight as 210 pounds, medical crew weights at 210 pounds. There's 310 pounds of medical equipment and 18 pounds of liquid oxygen. Total aircraft weight without fuel was 4,330 pounds. The spreadsheet then proceeded to tabulate the computed fuel load and cargo capacity. The load table listed max fuel load is 90%, 860 pounds, which will keep the helicopter slightly below gross weight and allow for no additional cargo passengers. The total aircraft weight with this load was 5,190 pounds, and the moment was 131.2 inches. The flight manual lists the max gross weight at 5,225 pounds. He was 35 pounds under gross weight. The rotor RPM gauge is a dual gauge representing engine-free turbine speed. The rotor RPM displayed using LED bars along the arc of the gauge. The gauge itself is approximately 2 inches in diameter, and in the accident helicopter installed in the lowest left portion of the pilot's instrument panel as shown on the slide by the red arrow. According to the airframe manufacturer, this is not the standard location for this instrument in this helicopter. There are no 337s on file at the FAA since the aircraft was destroyed in 2010. The documents have been removed. So we don't know if they moved it down there in accordance with an STC or if they had a 337, but for some reason it was moved down to the lower left corner. The commercial pilot was performing external load operations in the helicopter when one main rotor blade separated, which resulted in a loss of control and collision with terrain. The helicopter rolled downhill and the airframe sustained substantial damage. On-site examination of the wreckage revealed that 4 of the main rotor blades were fragmented into many pieces. The 5th main rotor blade was found about 900 feet from the main wreckage and exhibited less damage. Post-accident examination of this rotor blade revealed that it had separated due to fatigue cracking that had initiated near the root end of the blade at the second most outward bolt hole through the spar, skin, and doubler. The pilot stated he obtained an airframe power plant certificate so that he could perform the TE inspection. He added that he averaged about 200 TEs per hour and that he tried to comply with the AD as best as he could on work sites. On a typical job, he usually did not perform the TE inspection until he got home that night. Here's a picture of the rotor blades as seen at the crash site. The NTSB determined the probable cause of this accident to be the pilot/mechanic's failure to properly perform required inspections of the main rotor blades at the necessary intervals, which resulted in an in-flight separation of the main rotor blade to disbonding and fatigue cracking. Contributing to the accident was a lack of clear guidance in the helicopter's maintenance inspection instructions, which allow for the possible misinterpretation by maintenance personnel of their intent. We've all seen that in ADs before being misinterpreted because sometimes the ADs are a little vague and a little hard to understand. Lack of awareness. What's the safety nets for lack of awareness? Think of what may occur in the event of an accident. Check to see if your work will conflict with existing modifications or repairs. Ask others if they can see any problems with the work done. Norms. Norms in the content of the Dirty Dozen means our group has a better way to do this job than the published procedures. We call that tribal knowledge. It could be considered tribal memory, unwritten rules enforced by a group, peer pressure, or habits. In the case that follows, someone decided to reuse a castellated nut that was worn out and would have not come loose if they would have installed a cotter pin. You look up in the dictionary, you can find norms in the dictionary. And what it says, the definition for it is an authoritative standard, a principle of right action binding upon the members of a group and serving to guide, control, and regulate proper and acceptable behavior. A set standards of development or achievements usually derived from the average. A pattern or trait taken to be typical in the behavior of a social group. Widespread practice, procedures, and customs. I think that's how we most interpret it right there. In this accident we mentioned earlier under fatigue, but norms may have also been a factor. Improper use connection hardware began a chain reaction that led to the crash of a AS-350 on a sightseeing flight. The NTSB says a series of maintenance errors was responsible for the December 7, 2011 crash of a Sundance helicopter Eurocopter in the mountains east of Las Vegas. The NTSB says the pilot and all 4 passengers on the Twilight Tour sightseeing flight were killed in the crash. The helicopter was destroyed, and an NTSB meeting convened to review the accident. Chairman of the NTSB noted that research has shown that the primary category of maintenance error is failing to carry out necessary actions. Norms in play. Did the organization reuse self-locking nuts regularly without checking their self-locking serviceability? This is a self-locking castellated nut, which that tells you right there, it's 2 different locking methods on this one nut. So it's got to be a critical component right there. Here's a picture of what it should have looked like. The flight began at 16:21 local time when the helicopter took off at dusk from Las Vegas International Airport in VFR conditions with good visibility. The pilot planned to fly to Hoover Dam about 30 miles southeast and then return to the airport. The helicopter was not equipped with flight data recorders and they were not required. However, radar data from the FAA showed the helicopter had been level at 3,500 feet with a ground speed of 120 knots. Until about 1 minute before impact and then climbed to 4,100 feet, turned 90 degrees left and slowed. The helicopter descended to 3,300 feet, tracked northeast for 20 seconds before entering a left turn and plunged towards the ground at a rate of at least 2,500 feet per minute. The NTSB said in its final report on the accident, parts of the helicopter were destroyed by post-impact fire. The wreckage was found in a ravine about 14 miles east of Vegas. Maintenance personnel. The mechanic who installed the forward aft servo received his airframe power plant mechanic certificate on December 2008. Worked on maintaining general aviation airplanes and business jets before being hired by Sundance in June of 2011. After his hiring, he received NDOC training in record keeping, maintenance procedures, and use of the Eurocopter manuals, as well as on-the-job training, but he had yet attended any helicopter-specific training. His schedule typically included 4 days of 11-hour shifts, followed by 3 days off, 3 days of 12-hour shifts, and 4 days off. He estimated that he previously had performed about 6 forward aft servo installations before he began to work on the accident helicopter. He had been off duty on December 4th and 5th and initially was scheduled to be off on December 6th, but was asked during a telephone call at the previous afternoon to report to work. He said he went to bed about 2200, 4 hours later than his normal bedtime, but fell asleep around midnight, woke at 5 feeling good. He reported to work about 5:50 and was assigned the forward aft servo replacement, which he said performed without difficulty and without feeling rushed. The mechanic who inspected the servo replacement had been named a quality control inspector about 6 months earlier. He also was one of the 3 lead mechanics who directed maintenance tasks when management personnel were not present. He received a airframe power plant certificate in 2002. Like the mechanic, he was not originally scheduled to work on December 6th, but he was asked during a telephone call the previous day to report to work that morning. A review of the Sundance maintenance record showed that the inspector working as a mechanic in June 2011 failed to properly reinstall the chin bubble, portions of the windshield on the helicopter. Sundance determined the root cause analysis that the inspector's perception of the need to expedite the repair to avoid aircraft downtime was a contributing factor leading to the failure. So contributing factors were mechanics and inspectors' fatigue and lack of clearly delineated steps in the maintenance task of the inspection and the NTSB. Okay, what they found at accident site. The investigators found the forward aft main rotor servo control input rod in the wreckage disconnected from the main input lever. Its connection hardware was not found at the crash site. You can see by the red arrow that the hole exhibited no damage and there was no hardware installed. So what's the safety nets for norm? Always work as per instructions or have instructions changed. Be aware that norms don't make it right. The Dirty Dozen is a catchy title, but it's possible there are more than 12 human factor issues. These 12 are meant to stimulate the human factor discussion. What about illness, emotional issues, anger, pride, alcohol, drug abuse? Errors are part of life. Errors are natural and forgivable. It is the content of the errors that make them tragic. Maintaining and operating aircraft is the most unforgiving context. The reality we face in this injury is if we make even a very slightest mistake, it may well cause a fatal accident. As we've seen time and time again, it's always a chain of events that leads to an accident and not just one thing. Here's our email addresses. So if you've got questions or if you got information,